force directly and the displacement. So what happens is this. You raise it up, it's got a bit of a safety, so you can't squeeze it and drop it. But the proper procedure then is, if your hand's big enough, you can squeeze that and pull, and that if it's not big enough. But I can do that, it hits.
Okay.
And it bounces back, and you catch it. And the test procedure in the field is to basically work the plate in, do 3 drops to seed it, and then record the last 3.
Okay.
Some people like to record all 6 impacts, but there are ASTM standards for the testing as well as European standards for the testing. And so if you record 3 or 6, whatever, you're measuring the force and you're measuring the velocity response. The velocity response comes out of a, and to be safe, you can lock this off. In addition to the safety, you can lock it off. Those wheels, and you'll see a picture, you got a chance to print that out? I don't know.
Absolutely.
Yes.
Charles.
Computer and move. Can
Put it on the screen.
Well, the wheel's assembled, and you can kick it on to move it.
Yeah.
You tilt it over, then you're wheeling it around the job site to do the testing. Because that wheel's, the rest of the assembly's over there, but for today, we won't worry about assembling the wheels. He's got some pictures of it. And I've got a slideshow. So what it amounts to is, and this is the unit that we're doing it with, the NDE 360. You bought some of our equipment.
got a-
The one we have is
Freedom Data PC.
Freedom Data PC.
Okay.
So
It's,
this one is a little less flexible, but it still does a lot of tests with a compact flash and a touch screen. So the unit, and you can run it English or metric units, so if you hit an M, you switch it to metric. Now it's in millimeters. So this plate radius, this diameter actually is 200 millimeters. So it's a 200 millimeter plate. That would be for road base, gravel. You would use a 300 millimeter plate. You can change the plates for subgrade because it's a little softer and less stiff, less modulus. So now you probably know, are any of you pavement engineers?
actually, it's payment because we are civil engineers. We have work on payments. I have, we work with them.
Well,
work on
it seems that now
payments bridges are some of
the design has changed to where it's a mechanistic empirical pavement design, meaning they are using modulus to design the pavements based on the modulus of the subgrade or stiffness, the modulus of the road base, and the modulus of the asphalt, we probably say bitumen, or concrete. And you probably have heard about resilient modulus testing, that type of thing. So I'll tell you more about it, but we'll just demonstrate the test. So basically, you just turn on the unit and it starts. It's very simple that way. Change the date and time. It's not the right time, of course, but okay, fine. Nor is it the right date. It came from America. None of it's right.
One day behind.
Exactly.
Yeah.
Exactly. So it's got the force and a calibration and a velocity. Because when we drop this is the force transducer, and then there's a geophone inside, a vertical geophone, that's calibrated per the standard. You have to calibrate on a large concrete block. You have separate 3 points that measure the actual displacement. So the velocity signal gets integrated to be displacement with some signal filtering that's done on it all per the standard. So basically what happens when you test it is you've selected it. There's something called the soil factor. A mix, clay is a factor of 4, and 3.142 is a factor of stress concentration for a clayey sand or sandy clay. And for a sand, cohesionless or gravel, there's a smaller factor. And Terzaghi, way back in the 40s, looked at the stress concentrations under a round plate. And he came up with these stress concentration factors. The uniform stress was a mix of sand and clay. The hyperbolic, I'll get this wrong, one was parabolic, one was the other way, convex.
Yeah.
But it was basically whether it was a clay or a sand. And the uniform was a uniform stress.
Yeah.
And as I recall, the clay is the one that had the high stress concentrations at the edges. And the sand is in the center more so, the nature of it.
Yeah.
So, and that's in a slideshow I give. We give that slideshow, but it talks about it. So as we do the test, once it's all set up and calibrated, you say back. You can set a file name. There's already a name set, I'm sure, so we'll just say test. And it's got signal gains, those are normally ×1. And we just say test. So when I drop it, we should get
He's locked it off.
Yeah, I did lock it off. Thank you for reminding me. Good. So we got both an impact force and a displacement. Now we're testing on a carpet. It's going to be a little different
Yeah, of
Yeah,
than
course.
you'll see on the brochure.
Yeah.
But nonetheless, you get this peak force of, in this case, the absolute peak newtons. We're going to change that so you can see one more digit of newtons. We discovered that recently. But 99 newtons, and it is 0.969 millimeters. So it basically displaced a millimeter on your carpet. So that's record number one.
So
So
sort of the system is some similarities to the impact echo method. as
it
well?
is similar to the impulse response.
Impulse response. Yes.
Because you're measuring the force
Yeah,
and you're measuring
yeah.
response. Except the calculations are simpler right now, much like you may have heard of falling weight deflectometers for road testing with the heavy drop weights. Those machines also do simple static calculations. This is based on a simple static calculation of displacement and stiffness. So they aren't doing it dynamically yet.
Right.
Maybe in the future, but right now it's a static
Right.
calculation. The dynamic is
Equal
actually
static.
research
Equal
about it.
static.
So you're getting the stiffness of sound.
Yeah, and you calculate it actually, as you'll see as I do it, and it's ready to go. It's set up to test 6 times right now.
Yeah.
So I will just put in 6 tests, and it's easy enough to catch it. There's the second, similar results, 0.913, and that's the displacement, and that's the force. So as I do that, again, 3 results, and it's done. So this shows the 3 peak displacements, the average displacement, the soil stiffness in kilonewtons per millimeter, and the average modulus in MPa. So these are the results that are coming out of it. And all of that gets recorded on the compact flash. Now you can use our Windows-based software to analyze it again. You know, a laboratory might have a question about a result because they're typically doing quality assurance of new construction. That's what this is being looked at. I'm not sure how much you use nuclear density gauges.
A lot.
Well, it's being looked at as a nice alternative because at least in America, the nuclear density gauges have a lot of regulations.
Yes.
And so that makes it difficult for the laboratories and expensive because of the radioactivity and the regulations to be safe. So this is being looked at because of the change in pavement. Now I shared one other idea, which is in my slides, but I'll use your board, that I came up with an idea that a professor who's chairman of the civil engineering department at our University of Maryland, close to where I'm at in the Northern Virginia, Washington, D.C. area. Our main company is still in Denver, Colorado, but I'm actually on the East Coast now, in Washington, D.C. based.
Okay, sure.
So what I thought about, because I'm a geotechnical engineer, I have a bachelor's and master's from the University of Texas at Austin, and I worked 5 years doing conventional geotechnical materials and pavement engineering before specializing into non-strict valuation, geophysics, structural monitoring, things like that. Well, my idea was simple, because of the Proctor mold and the Proctor compaction curve. Nobody apparently had ever thought of this, but you know you get a curve where you have the dry density versus moisture, right?
Yep.
And we're always working against the zero error voids curve,
Yep.
and you get a point. If you do a 5-point curve, you get a better curve, but nonetheless, standard curve. And it's either in what we call a 4-inch, which is a little over 100 millimeters, right?
Mm-hmm.
Mold, or a 6-inch. And 6-inch is typically the road base, the gravel
Oh, yeah.
type mold.
Yeah.
So what I told them, and I did it with the laboratory, and I shared it with the professor, I said, well, why don't we just plot stiffness or modulus versus moisture? So it turns out, because that 100 millimeter diameter, in America at least, we do use a, can't be me, somebody else. It's the wrong time in America for my phone to ring. It can ring here, but I don't think it's going to. It's a little later. So anyhow, what I was saying is, it became, so what I did in the laboratory, I took a smaller plate, 100 millimeters or 150, and tested on the 4-inch or 6-inch molds. And then it was just like a piston. So we got a stiffness at each point.
Just bring
And that
5
stiffness
minutes to
out of this curve
405,
was
right?
proportional
405. I'll introduce another
to
person
the
as well.
resilient modulus that
The
they're
big
using in
block.
pavement design in the
Yeah, fourth
laboratory.
floor. Yeah, fourth floor.
So they've proven this in their research. So the next step is to make a correction for the stiffness. Just imagine that we're sitting here, well, it's not quite big enough, But you know what a proctor mold looks like, right? About like this. And so that plate goes right on top of it. We do the test, the weight drops, and you get stiffness at each moisture content. Are you with me? So now you've got a modulus or stiffness versus moisture curve as well. For a standard test that is done on materials routinely to get the optimum moisture and density of compaction, right? So this relationship is working, so now you have to correct for this confined modulus, because this is all soil. It's confined. So now what they're researching this fall is unconfined. What is the correction to go from the laboratory to the field for these materials? And so that's the next phase of the research. It's a $400,000 study on how you develop standard testing protocols for the test. And that was my, I'll say, somewhat brilliant but obvious idea that nobody else had done. So I said, okay, we should have a curve in the lab that maybe then you can correct it for the field. And that's going to make it easier to use the test than it has been done previously.
You've done work on porous materials.
Yes, porous materials.
Porous medium, and that it's got some
So it's
applications.
really depending on water content of the
Oh, yes,
soil.
it does.
So when the time you load it, whether on the top is permeable or not permeable, you are getting different results.
Yeah, and in fact, the material I personally tested was a very clayey sand.
Okay.
And the modulus curve looks like this, drops out of sight. This is 4 times what this is, 1 times,
Yes.
because of the clayey nature of that material. So it's very sensitive to the moisture.
That's right, because the dynamic stiffness you're getting
Yes.
is much higher than it's like called static test. Because of the test you load it, so all the water will come out.
Yeah.
Ultimately. But one time you have an impact.
Right.
You have a fluid pressure on that.
Well, and what's important to understand is what they've done in the research so far is that the LWD for lightweight deflectometer
Okay.
values of either stiffness or modulus, and these are just related by constants. They're the
Okay.
same. They're just related by constants.
Mm.
That relationship goes to the resilient modulus. And the resilient modulus is a triaxial test in the laboratory where you're cycling it and confining it. It's a confined cycling test to get resilient modulus. And so that information, what's interesting to me is that one PhD is graduating now who proved that that worked. That the test here was relationship to the resilient modulus.
Yes.
So that closes a big gap. Now we want to be able to take the same stiffness and correct it for being on the ground and not confined
Yes.
versus being very confined in the cylinder.
Yes.
And what was so convenient, and I don't know, does anybody here know the size of your Proctor molds? I think they're all
They're
the
exactly the
same
same
around
as,
the world.
yeah, they're the same as
So
the
it works
ASTM
for you
standard.
too,
Yeah,
because 4 inches is like, what is that?
102.
That's 101.6 millimeters.
Yes.
So it's like a piston. The 100 millimeter plate goes right inside. And the 6 inch is 152.4 millimeters. So the 150 goes right inside. Very convenient. It's the one time I've seen English and metric be very compatible. Otherwise, they're never compatible.
You use CBR test and all that here, so all
Yes.
Same standards, yes.
and all
I thought they
that.
were probably
No,
were,
actually,
just because they need to be a certain volume of material to be the same test.
Yes. So another important thing
Yes.
is repeated loading. Say because of human, you have track control.
Well, that's certainly the resilient modulus part.
Yeah. Repeated loading.
Yes.
What your test, you have to be closely reproduced.
Yeah, but what it amounts to is people will have a laboratory curve. You're still going to have to control the moisture. You
Yes.
still need to measure the moisture in the field
Okay.
to control it.
Correct.
You're still going to have to do that. And there's a German device that's a pretty good field oven. There's a Sir Speedy moisture test. There's a variety of ways you can measure the moisture still. But you're getting away from the nuclear gauge, and you are getting to, because the new pavement design, and I wonder if this is true in Australia, I imagine it is moving to designing based on resilient modules. No longer the old
Yeah,
pavement
it's just
design
more
approach.
performance-based type.
Yeah.
Exactly.
Performance-based.
And because of that,
Correct.
I just tell people simply, modulus matters.
Yeah.
So
Correct.
now if we could measure modulus in the laboratory in the field,
Correct.
relate that to the expensive resilient modulus testing,
Yeah.
then you've got a.
We
closed loop.
went to what's called AS5100, our standards. We are moving towards the bridge and the road design standards, moving more towards the performance based.
Yes.
Not totally, but yeah, moving towards
Yeah, they
that.
call it in America
Yeah.
we say it mechanistic empirical pavement design.
Sure.
Meaning it's part modulus, it's still a little
Sure.
empirical.
And we use the ASTO a lot, ASTO
Yeah,
standards a lot.
exactly.
Yeah, yeah.
And so we're excited about this. That research, the professor's name, and I know him well because we've loaned him equipment and he's close to me. And I gave him my idea. He liked my idea. I couldn't figure out how to patent it, so I said, okay, I'll just give it away. But his name is Schwartz.
From, you said...
University of Maryland.
Oh, you said
Maryland, MD, we abbreviate it, Maryland.
Yeah.
And his first name is Charles,
Okay.
or Chuck. Name Chuck? Just Charles.
I think he's written a book. I think he's written a book on beauty.
He's very good at pavements. He
Yeah.
probably has.
I've seen one of some of his publications.
Yeah.
Yes.
So he's a senior
Yeah.
professor. He's
Yeah,
chairman
yeah.
of the department.
Yeah, he's not well known yet.
He's,
Yeah.
he's a few years older than I am even. I'm getting up there now. But anyhow, I thought you'd be interested in that, and obviously you are a little intrigued by that. And we've got some brochures. I had, I guess, Charles printed it out. See, I'm going to call him Chuck the rest of